Okay, this is the latest version of the MNIST Digit classifier, and it's taking some of these 120,000 different digits. I think it's written by Jan LeCun, and this is the test set 10,000, and it's running it through a neural network, which is 3 layers deep. It's probably a little bit more complex than you'd need, because it's got a lot of optimization code in. But if I hide that, I'll show you what this means. Actually, these shouldn't be hidden, I think, because these are the parameter updates. So if I close that down, then you'll see basically the structure of it, which is layer 1. It's a batch run, so it's looking 10 digits at a time. These are the 10 inputs. These are the inputs, or sorry, the weights for layer 1. This is the gradients for layer 1. That's the update, which is basically, it's got a little bit of extra code in there whether you decide to take the optimization or not. But effectively, it's taking the gradient times the learning rate and adding it to these parameters. This is layer 2. And finally, this is layer 3. So layer 2 is 15 neurons. Layer 3 is 10 neurons. And then there's a softmax cost function at the end. So back on the dash tab, this is run for 70,000, and it's been taking lots of different inputs. So if we do a quick run of, say, I don't know, 250 digits from the test set, and we run a test, take a little bit of time to set up, because my Visual Basic code is so poorly. But what it's doing now is it's flipping to look at digits from the test set, and it's not going to pull 10 individual numbers at a time. It's going to pull just one, but replicate it, so you can actually see what the digit is and decide whether it's getting it right or not. But it's slow to calculate because there's so much on-sheet code to support the charts and to support the printing, etc. The setup was pretty slow when it does a full recalculation. So here it's looking pretty good, 96%. These are the letters written by the human from the test set, and this is the guess that the computer's making based on what it was trained with in that last 70,000 runs. My chart doesn't go to 70,000 because I only built in space for 2,000 tests. So it's looking pretty good. It's 96% accurate at 250. So I'm wondering if I can speed up the learning dramatically. And my idea is to exponentially decay the learning rates, because I had heard a YouTube video with Jeff Hinton talking about this. So I'm going to give it each 1,000 iterations, I'm going to half the learning rate, and I'm starting at 1%. I'm going to use all of the optimization I can, because I think it's worthwhile, and I'm going to do 20,000 of these. So that's 20 different steps, and that will give me 20,000 results. So that means I can record my progress every 10. Well, that actually won't matter because I'm going to obliterate the individual run each time. So I need to fix my code now. So back on the VBA that does the update, in one of the modules I've got a step test and train. So I'm not going to test it every 1,000. I'm going to do something slightly different, which is I'm going to take the range of the learning rate, and I've spelled that wrong, so that was never going to work. So I'm going to take the learning rate and I'm going to divide it by 2. Simple as that. So every step it'll half the learning rate, and it will give me quite an interesting plot at the end. So I'm going to kick that off, step, and I'm going to leave this and then come back to tell you what goes on. Aha! I haven't reset or initialized my training data, so I think this is going to start with the fantastic learned parameters we had before. So this may not work, but let's see if my code was clever enough to reset to initialize it, which I don't think it would have been. Iterations range, initialize. So I did initialize, great. So we are actually in good shape. So it's going to start from gibberish. And what that means is, as the 10 numbers are extracted from the data set and presented to the model, it hasn't got a clue. It seems to think they're all 2s and 7s, because it's got no pattern recognition ability stored within the parameters that were trained on the 70,000, because we wiped them out, we set them all to random. But we're already seeing in the first 100 iterations that it's at about 17% accuracy, which is pretty good. 1 in 10 digits should be 10%, so it's already climbing above that. But this is going to take a while, so I'm going to nip away and report back how quickly, hopefully within 1,000 times 20,000 iterations, how high we can train this neural network to. So I'm going to pause now and come back in a little bit. Well, that didn't go to plan. I have just been away from the model. Actually, I've been canoeing in mangroves in the tropics for an hour in these uncharted waters. Well, uncharted by me at the bottom of the garden, which was quite exhausting. And I come back to find this disappointment. I'm assuming that the initial learning rates were too harsh and the gradient descent jumped all over the place. And then the final gradients are just rubbish. I mean, they're just too small. So maybe I run it with larger steps, or maybe I stick with the other patterns. If I just, I've got some recordings here. So these are previous runs, and if I just tell you what happened here. So here we're looking at 0.1%, and it learnt up to 90, and that was no changes, but with Momentum and RMSprop. Another version. Sorry, to go back, this was some crud I was training, testing. But this one is with even less, so I went down to half of 0.1%, got to 91%, so that's pretty good, in 50,000 iterations. Right, well that was the last one that did 70,000. But you see a much broader curve with 0.001, 86, 83 when I just had RMSprop, up to 10,000. So it's quite interesting. So I've run it a few times, but this was the most feeble. Anyway, I shall continue to play and report back.